This video is going to go through the solution for problem 5 in your problem packet. As always, I want you to make sure that you read the problem yourself, try it yourself, pause the video while you're doing that, and then come back to the video to see the solution or explanation or get hints. So problem 5, we have this record, diameter is given, initial speed is given 70 revolutions per minute. It says the motor's turned off, it takes 3 seconds to stop. Part A, find the magnitude of its initial angular velocity in radians per second. So go ahead and pause the video, try it on your own, and come back to see the solution. This is in essence a unit conversion problem. You have 78 revolutions per minute, you need to get a radians per second. So first we convert revolutions to radians by using our conversion factor 2 pi radians per revolution. We have to get minutes to seconds by using 1 minute for every 60 seconds, so we get 8.17 radians per second. Part B, I want to find through what angle in radians does the record rotate while stopping. Again, pause the video, try it, and come back. In essence, we're looking for an angular displacement, and you have all sorts of choices for your angular displacement. Pick your favorite equation. I'm going to use my favorite equation. Delta theta equals omega bar t, just like delta x equals v bar t. I use this because it's easy. Omega bar is omega naught plus omega final over 2. The initial speed is given as 8.17 radians per second. The final is 0. Divide by 2, multiply by 3 seconds, and you get 12.3 radians. If you had gone and found the angular acceleration and used one of the other angular displacement equations, I'm sure you'll also get 12.3 radians within rounding. Minor differences here and there. A little more complicated to use that one, though. Part C, a little more involved here. I want to consider a point on the edge of the record. When time is 1.5 seconds after the motor is turned off, I want to find the magnitude of all these things. Tangential acceleration, that's our usual acceleration. Its centripetal acceleration, and magnitude and direction of its total acceleration. In other words, the combination of tangential and centripetal acceleration. So I start you off here by reminding you that A equals R alpha. This is a connecting equation from our linear or tangential acceleration to the rotational acceleration, which you may have found in the previous part, but at some point you have to find it here. And so pause the video and start working on this, and I'll lead you through it step by step. So first, if you want to find alpha, it's omega final minus omega initial divided by t. Again, you may have done this in part B, but here's what you would do. And so it's 0 minus 8.17 radians per second divided by 3 seconds. Then we get negative 2.72 radians per second squared. Even though we're looking for a magnitude, we should still continue to use the negative sign. It's saying, of course, it's slowing down. It's losing speed at a rate of 2.72 radians per second per second. We can now use this to find the tangential or linear acceleration. Keep in mind, of course, that you were given the diameter of the record, and also it was in centimeters, so you have to convert it to meters, so that's 0.305. You have to divide by 2 to get the radius, which is r in the equation, then multiply with that by alpha, the angular acceleration, to get the negative 0.415 meters per second squared. And again, even though it asks for the magnitude, it's still a good idea to leave that negative sign on it just because it's saying it's slowing down. Certainly if you took it off and took the absolute value, that does completely answer the question, but we will certainly need that negative sign later on in the problem. The next part is finding the centripetal acceleration. You recall in class we derived is v squared over r. The v here is the tangential speed. And here you probably want to use the connecting equation that v is equal to r omega. It's a good idea, I think, to combine equations, although if you didn't go through this derivation I'm about to go through, it's absolutely fine as well. If you do put the r omega in as v, you get r omega squared over r, which then is r squared omega squared over r. One factor of r cancels, and you have that centripetal acceleration equals r omega squared. This is not a new equation, although the book certainly makes use of it. It's just a really useful reinterpretation of the centripetal acceleration equation. The question becomes, what angular speed to use? Well, if we're looking at the instantaneous centripetal acceleration 1.5 seconds into the motion, we have to use the angular speed that is 1.5 seconds into the motion. So that means we have to find the angular speed. It's not going to be the angular speed with which the record started moving. How can we do that? Well, we can use omega final equals omega naught plus alpha t. We know the initial speed was 8.17 radians per second. We already found the angular acceleration, the angular acceleration at negative 2.72 radians per second squared. Multiply that by 1.5 seconds. So we have the new angular speed of 4.09 radians per second. Now, if you had just done this by inspection, that would also work considering this is 1.5 seconds into the 3-second slowing down phase of motion. And of course, if it's halfway to the end, it's going to be halfway from its initial angular speed. So if we just took the original 8.17 radians per second divided by 2, you get 4.09 radians per second. And that would make absolute perfect sense if you'd used that. So we put that into the centripetal acceleration. Again, keeping in mind we have to take the radius of the record, not the diameter. And we should be getting 2.55 meters per second squared. All that remains is to put the two components together to get the total acceleration. Here's a picture to help you visualize. We're looking down at the record. We'll say that maybe it's going in a counterclockwise rotation, and we'll pick a point on the edge. We'll draw the vectors for the two different types of acceleration. So here's the tangential acceleration, pointing backwards, right? It's rotating this way, and of course the tangential acceleration is going to point opposite to motion. Here's the centripetal acceleration. You'll recall, of course, centripetal means center pointing, so of course it points to the center. And all we have to do is put these together as vectors. Right now they're tail to tail. We don't do tail to tail, and that's certainly not going to help us out. We want to find the angle, so I'm going to put them tail to head. Doesn't really matter what order you put it in. I did centripetal acceleration first, tangential acceleration second. The blue vector, of course, by combining accelerations, represents the total acceleration. And the angle is always the one near the vector, beginning of your vector diagram. So I started in here. Certainly if you had done tangential acceleration first and centripetal acceleration second, you'd find the angle over there. It's fine. Nothing wrong with that. And here it's just a matter of using Pythagorean theorem to combine them to get the magnitude, and an inverse tangent or another inverse trigonometric function to find the angle. Here I've described the angle as an angle away from the radius. The centripetal acceleration points along the radius. It is an angle away from that radius or radial vector. You can consider that.